Layer. As this picture is illustrating, the MAC layer is about cabling. The goal of the MAC layer is to interconnect systems, and it was designed at a time where most of the systems were interconnecting with cables. Although we will see it has a lot to do with radio systems, but that's perhaps a different story. This is the roadmap for today. We will talk about what the MAC is. The MAC layer is a bit paradoxical, and as I alluded to several times, in some sense it's not necessary. So it adds a lot of complexity to the understanding of how TCP IP works. In order to understand why it is this way, we will exceptionally go a bit through history and explain how the MAC layer converged to what it is today. So we will do a bit of evolution of the MAC layer. That will be point 2. As usual, in order to understand something, it helps if we try to understand why it was invented and what problem it was solving. The MAC layer was invented to solve this problem that's illustrated here. Assume you cable several computers on a campus, for example, by connecting them to the same coaxial cable. Very few people would do that today, although we find some instance of this in cable TV distribution networks. But at the origin, this is how the first Ethernet networks was done. There were a small number of computers in one campus connected to a big cable that was used to interconnect all the computers together. There were other forms of interconnection of computer networks at this time. We're talking in the 80s. They were based, for example, on telephone switches. You have telephone cables on practically all enterprises and campuses. So you could connect your computer with a modem to the telephone system. But the drawback of the telephone system is you need to set up a call from A to B, and then computer A talks to B. But if computer A wants to send one packet to a computer C, another one, then it needs to tear down the connection, bring another one, etc. It's not convenient to use the telephone network for direct interconnection of computers. Therefore, people thought about having a shared cable to which you connect all the systems together. Now, if you do this, there is a problem of collisions or interference. If you have several computers that send a packet at the same time on this wire, the packet will propagate through all the wires. If there's only one, that's fine. But if there's more than one that are overlapping, there will be very likely a collision. A collision means that if several systems talk together, if we use the naive approach where let systems talk together, it's impossible to decode. It's not strictly impossible to decode, and modern information theory and communication theory have developed means of joint decoding. Joint decoding is if several systems speak together, talk at the same time, by trying to detect on which frequency hopping system they are, or by trying to detect some pattern in the way they speak, it might be possible to decode the two. Like if two people are talking in the same room, if you're whispering to your neighbor, I am talking, your neighbor is talking, probably you can tune to one of the two, hopefully me, but it's not guaranteed, and listen to and decode in spite of the other that you treat as noise, because there is redundancy in the signal. So the same trick can be applied for joint decoding. The prototype of technology that use this is the 3G networks, CDMA. But it's very complex. It has a lot of drawbacks. In particular, it requires power equalization, a number of things that make it not so desirable. But I would say this is the state of the art in multiple access today. In local area networks, we want to do things simpler. Plus, when this was invented in the 80s, those joint decoding things were not yet well known. So the more computer science way of doing things is called mutual exclusion. Find a way to prevent several systems to talk together. For example, by having a master, in principle me in this room, who has the token to speak, and if somebody wants to speak, raise your hand, I give you the right to speak. This is a token passing scheme. That's an example of a mutual exclusion algorithm or protocol that prevents collision. So that is the problem that the Ethernet wanted to solve. Now, Ethernet added a twist to it, which is we want it to be distributed. A token passing scheme like I just described would be, which is also called a polling scheme, is based on having a central station that would pass the right to speak. Now, this is not distributed. Distributed means we would like that those 4 computers implement an algorithm, hopefully the same, and the emerging property of those 4 together is a mutual exclusion algorithm. This is what Ethernet wanted to solve. Ethernet and others, there are many variants of MAC, so medium access control, that's the name of this mutual exclusion protocol, exists in various forms. The form that is most common today is Wi-Fi. Where is Wi-Fi? Here. Ethernet still exists today, but as we will see, Ethernet might not be exactly a mutual exclusion protocol. We'll come back to it. The historical Ethernet is CSMA-CD that I will describe in a few more seconds. Today, the systems that continue to use such mutual exclusion protocols are the local area wireless networks and also the power line communication. When you use the electrical wires for communicating, you have problems that are very similar to those of wireless networks. What we will describe now is the protocol called CSMA CD. Sorry, this is a bug. It's not CSMA CA here. It's a D. CSMA CD is the name of the mutual exclusion algorithm that is implemented in Ethernet. For many people, it's an equivalent to Ethernet. It itself derives from another idea, very simple idea, which is the Aloha Protocol. It's a historical protocol. It's not used anymore, except in very, very simple situations. Aloha stands for hello in Hawaiian language, I believe. And it was a protocol that was developed originally in a computer network environment in the 70s, where there was 1 computer per island. So here you have 5 boxes. Each of them is 1 computer on an island for the happy people who live in those regions of the world. And of course, you would not pull wires here, so you would do things wirelessly. This was the 70s. So in the 70s, computers were mainframes, centralized computing. So you had peripheral systems that wanted to connect to a main computer on the main island. And the way they did it was to use this algorithm here, which is in fact very simple. To understand it, we need to know that there was 2 radio channels used in this system, one for communicating from the periphery to the center, and another one from communicating from the center to the periphery. The mutual exclusion problem exists only in one direction, from the periphery to the center, because when the center wants to communicate, it, of course, will not create a collision. It talks to only one device at a time. But in the reverse direction, when several remote machines want to talk to the center, there could be a collision if 2 packets overlap at the receiver. How is that managed? Well, it's not managed. You just let things go and detect if there is a collision. So whenever you send a packet from the periphery to the center, you simply send it and you wait for an acknowledgement. If there is a collision, that is very minor, perhaps this packet can be decoded. If there is a strong collision, this packet cannot be decoded, and the packet is lost. By detecting, you will detect that it's lost, as usual, by seeing whether an acknowledgement has come back or not. The acknowledgement is assumed to come back on the other channel on which there is no contention, so there should not be any problem here. If there is a collision, then it's probably because someone else was transmitting at the same time. What should you do? It's like you start talking in a room and two people start talking at about the same time. If they are polite, they will back off. They will say, oh, I'm sorry, please go ahead. No, please, why don't you start, etc. So here's the same thing. If you detect that there is no ACK, which you detect by a timeout, you retransmit. Of course, if you retransmit immediately, you will recreate the collision because the other guy might do the same thing again. So the computer equivalent of the polite deferring, please do, is to wait to draw a random back-off time. And because it's random, depending how it's chosen, with some strong probability, with large probability, the other guy who was creating the collision will draw a different back-off time, and one of the two will speak together. This is Aloha. It's very simple, and it's based on, it's very typical of computer science. You try to do things optimistically, and if it fails, you try to recover from the failure, instead of first trying to organize everything and make sure you're the only one to speak. This is very simple. That's probably the only beauty of it. It also has generated a large number of research papers. And if you do a stochastic model of this and you try to understand whether it's stable, whether the number of collisions will not increase, a potential problem with that is if there are more than two that are creating a collision, they will back off. But if with some probability they will retransmit, which will recreate another collision. So you might be caught in a trap where you're always trying to transmit, and by trying and retrying, you never manage to transmit. This is the stability problem of Aloha. In a nutshell, if we assume that the transmission requests are completely random, mathematically if they arrive as a Poisson process, then this protocol will work, it's possible to make it a stable version of it if the utilization is very small, if the utilization of the channel is less than 18%. That means that most of the time you should hope that nobody's talking, and then for the rare cases where there's a collision, this protocol will be able to recover them. That is Aloha. Why is it interesting? Well, because it underlies what we will see next. It is still used in situations where, typically when you're bootstrapping some communication, if some systems are booting, for example, and you want to run a protocol to organize them together, at the time they boot, you may want to use something like Aloha for avoiding collisions while having something lightweight. It's used, for example, on the cellular telephone signaling channel in cases when you change cell and things like this. Today, we use a bit more sophisticated variants of this, and the first obvious improvement is to listen. When you send, instead of simply sending, crossing the finger and hope it works, if you are in a situation where you can hear at the same time what happened in the channel, and if you believe that you can hear the collisions, then it's better to listen before sending. And this is called CSMA, Carrier Sense Multiple Access. Carrier is the radio frequency on which you're transmitting. Carrier sense means you listen to the carrier. If you hear some activity on the carrier, you don't send yet. And that gives this algorithm. The only complex thing is the 4-letter acronym. You listen to the channel. If the channel is free, you send. Otherwise, you wait until it becomes free. And once you've transmitted, once you've sent, you will do the same thing as Aloha before. This is called CSMA. It makes sense only if the carrier or the channel is what we call transitive. If it's possible to hear everything or almost everything that happens on the channel. If the station on the left is very, very far away from the station on the right, this might perhaps not be the case. Then there might be a transmission here, another transmission there, and then you don't hear the collision. If that is the case, CSMA is not a good idea. If you are on a wireless channel where you have such a thing, then multiple access is a very, very difficult problem. And we'll see how Wi-Fi handles this. Right now, the assumption that is done on Ethernet, on this big cable, is that the cable is not too long. The original Ethernet cables were at most 1 or 2 kilometers, such that anybody can hear anybody. So you don't put on the same cables two systems that are supposed to speak together, but are not supposed to speak to the other end. So the system should be designed in a way that when anybody should be able to speak to anybody, which is in line with this idea of a completely distributed system, as opposed to the Aloha system, which is centralized. So this is what makes sense for this environment. A quick question now. Assume that we have a transitive system, so a cable that is not too long, where the transmitting power of every station is large enough so that anybody can hear whether anybody is transmitting. Can we avoid collisions? What do you think? I close the poll. So most of you think collisions can occur regardless of the bandwidth delay product. Let's see where the truth is. The answer is yes. And a simple way to understand this is to do a space-time diagram again. Here time is flowing vertically. I'm showing the two ends of the cable, A and B, and I'm showing what happens when A transmits a packet. The propagation time is small, but non-zero, so there will be a delay. When A starts to transmit, it is possible that B does not sense the carrier as being busy because the first bit is still on its way towards A, but it has been transmitted. So B transmits because it sensed the carrier idle, and then there will be a collision. The collision is at all places on the cable where those two parallelograms overlap. So the collision will occur here, not because of just the bandwidth delay product, it's really the propagation time itself that matters. If we have non-zero propagation time, which is practically always the case, except if you're on the same machine, I mean, two blocks of memory on the same computer, perhaps we can consider that there is no propagation time. But here, it certainly is not the case. So there will always be collisions. So CSMA can avoid some collisions. Of course, it will avoid some, but not all. And the collisions that cannot be avoided are the ones that occur when somebody transmits and someone else transmits in a window of time which is bounded by the max propagation time over the cable, which for local area networks of 1 or 2 kilometers is in microseconds, which is small, but for computers, a computer has time to do lots of things in 1 microsecond. So CSMA itself does not guarantee absence of collisions. So what does Ethernet do? It says, well, there can be collisions, let's detect them. We can detect them with an ACK, like Aloha does, but Ethernet does something slightly different. It detects the collision at the source. So CSMA CD, collision detections, means you wait until the channel is idle, you send a packet when it's idle, and you wait until either you have finished transmitted or you have sensed a collision at the receiver, at the source of the packet. If you have sensed a collision, then there is a collision and your packet should be retransmitted. You back off, compute you compute a back-off time, and you try again. There are additional details, like you send jamming, that we can ignore for a second. I will explain in a second. Here is a space-time diagram explaining the same thing here. So A starts transmitting at time 0. B listens to the channel, detects nothing, therefore starts transmitting, and sends some data. Then, as soon as B receives the data from A, it stops transmitting, or more precisely, it continues to transmit. Those are the so-called jamming bits. Why would anybody care about doing this? You sense a collision and you continue, so it's like being nasty, right? You've crushed somebody's foot and you continue pressing. Yes?
To let everybody know that there is a collision?
Exactly. It's to make sure that the collision is not ambiguous. Because collision, I mean, everything that the physical layer does is probabilistic. You measure analog signals, there's noise on them, so receiving one bit of collision, for example, might not necessarily lead to the same decision for all systems. So perhaps B has sensed the collision, but another system would not. So you just send enough, a collision that's long enough to make sure everybody, and in particular A, will sense the collision. So that's the only reason. And the protocol says, then what does B do? Well, A does the same thing. A senses also the collision and also sends the jam bits. And then the protocol say A and B back off, so they draw a random time, T2 and T1, and with a very large probability, the times will not overlap. In fact, the time is a multiple of the round-trip propagation time, so that if they don't draw exactly the same, they will certainly not overlap. And at time T2, then B will start transmitting. And because A is still in the back-off state, A is silent, doesn't do anything, and the collision will be solved. When A wakes up here, A senses the channel busy, therefore A will not transmit until the transmission by B is finished. And after transmitting, B will insert a gap between the two frames to make sure anyone else who is waiting on the end of the transmission on B will not create a collision. This is CSMA-CD. This is Ethernet, invented at the end of the in the middle of the 80s, and is still the Ethernet that we have on all the Ethernet plugs and sockets we have today. A small side effect of this is that in order for Ethernet to work, we assume that the medium is transitive, that anybody can hear everything. But in addition, we detect the collision at the source. Therefore, we must be sure that we are not in this scenario, but always in that one. So what is this scenario? This scenario is an example of a collision of a very short packet that is not detected at the source. This guy sends a packet. This one also, there is a collision. So whoever is in this area will see a collision, but A will not, because the propagation times are large enough compared to the transmission time of this packet. That occurs only if you send extremely short packets. If that can happen, then Ethernet will fail. A will think that this frame has had no collision, but if the intended recipient of the frame sent by A was C, for example, C will not receive it properly. It will not be able to decode. What's the solution that Ethernet decides? Ethernet says, well, solve the problem by forcing the frame to always be long enough. So the blue frame should be long enough so that any collision can be detected. Long enough means the transmission time of the frame should be at least as large as the the round-trip propagation time, which means that the size in bits of the smallest packet you can send should be at least as large as the famous bandwidth delay product. So we impose minimum packet size. Now, how can we impose a minimum packet size, which for Ethernet is 64 bytes, 512 bits? If you have just 1 bit to send, well, you will need to do padding. You will add dummy bytes to your packet to make it long enough. Of course, that assumes that the things that are contained in Ethernet frame have a length indication, which is the case for IP packets. If you put an IP packet in an Ethernet frame, there is in the IP packet header an indication of the length. So if there has been some padding, you will know that the IP packet is concerned with only a subset of the bytes. Now with IPv6, it's very unlikely that you need padding because the packets are very long, but with IPv4, it can happen that you have packets that are less than 64 bytes. 64 bytes means the bandwidth delay product is less than 64 bytes, which means that the size of the network multiplied by the bit rate of the network should be upper bounded. For example, if the original Ethernet, which was at 10 megabit per second, had a limit of 2 kilometers. So we could go 2 kilometers at 10 megabit per second. So you can still do this if you want to interconnect your chalet to your garage in the mountain and you have a very large estate. You can pull a very, very long Ethernet cable. As long as it's less than 2 kilometers and 10 megabit per second, it will work. Now, if we go to 100 megabit per second, which is the standard Ethernet today, we multiply by 10 the bit rate. If we want the same bandwidth delay product, we have to divide the total length by 10. So this will work only at 200 meters per second. If you are gigabit per second Ethernet, then it would be shorter. But as we will see, gigabit per second Ethernet is not Ethernet. There is no CSMA-CD. The original CSMA-CD was this one. It was on coax cable. Why? Or there were variants of it, like AppleTalk, which was on twisted pair cables. Coax cables have better shielding properties. You might remember from your young years and electromagnetic that if the Faraday cage effect, if you put a metal ball inside the metal ball, every external radiation will not come into it. The coax cable is an approximation of this. You put a metallic cover all around, so all the electromagnetic interference, in particular interference that is very frequent, is the interference of the next cable. You have an Ethernet cable, close to it you have another Ethernet cable, then the signal on one cable, you would like very much to come to the signal on the other cable. So you protect this by putting a shield here, and that is, I would say, the historical Ethernet. The beauty of it is you buy an Ethernet adapter, you cable the systems together. There is no switch, there is no hub, there is no nothing. There are just cabling, and it works. Some people may remember that. You have versions of that with the very old Macintoshes and AppleTalk printers. You would also wire with twisted pairs, telephone type of cable. You put them together, and they work. Essentially, that's the trick. They have something like CSMA-CD. As we will see, CSMA-CD is very seldom used, only if you have a very special case, but usually today we'll use other mechanisms that are called switches and bridges that we'll see in a minute. But something similar is used in Wi-Fi. For example, here A and C want to connect to a base station B. Then the problem is exactly the same with a small catch, is that here we're not in a fully distributed manner. We can run Wi-Fi in a fully distributed manner. It's called the ad hoc Wi-Fi, but it's relatively rare. Most of the case, we go to a base station. So base station is a central point. A central point does not necessarily have the hypothesis of transitivity. Transitivity means if A is able to send a packet to the base station, it does not necessarily mean that C is able to receive it or to see that the packet is being sent. So the CSMA-CD protocol will not work well in such a case. Wi-Fi tries to fix the problem, does not fix it entirely, but tries to fix it by using what is called RTS-CTS. This is cut and pasted from the textbook that we use, so it's a bug, it's not RST, it's RTS. So before sending something, you send a small packet, and this small packet is repeated by the base station. So if A is trying to send and B receives this RTS packet, C will see that A is trying to send because this will be amplified, repeated by B. So this is a way that Wi-Fi tries to make the medium transitive. It does not always work. You can have contorted scenarios where this alone does not work, but that's the basic idea. If it doesn't work, Wi-Fi does not work well, and you know by experience that Wi-Fi does not always work well. It works well in the nice situation where the base station is well in the middle of the room and everybody can see it without any obstacle. One of my favorite questions on this topic. Assume this Wi-Fi network with a single Wi-Fi channel and a single base station. How many frames can be transmitted concurrently? Concurrently means in parallel, occurring together at the same time. I close the poll in a few seconds. And the majority thinks at most one in total, which is the correct answer. Wi-Fi is, like CSMA-CD, a mutual exclusion protocol. That means on a given channel, there will be only one transmission that is possible at the same time. Even though perhaps the base station has two antennas and could receive from A and C, but this is not what will happen. If A transmits to the base station, this will force the channel to be perceived as busy at C, even though physically it will be possible to make it differently. Cellular networks behave differently, but Wi-Fi, which is the descendant of Ethernet, operates in this way. This is why the classical approach to Wi-Fi is to have an access point being cabled with Ethernet. So this base station is probably connected in the back end with an Ethernet so that you don't have several base stations that are competing together. Because if you have several base stations that are trying to relay the traffic for one another, there will be only one packet transmission possible at any point in time in the entire local area network, which of course will give bad performance if you have a large system. Why not two? Because they're using the same channel, why not answer two? So why isn't it possible to send from the base station to a mobile while sending in the other direction? Again, because it's the Ethernet model, there is a single channel. We're sharing the access to this channel. Whoever tries to transmit has the same role from the Wi-Fi viewpoint. Which is perhaps not optimal, but that's the way Wi-Fi is. Again, cellular telephony and cellular networks for data do things in a different way. In cellular networks, it's possible to send to the base station while receiving from the base station, but with some technologies.
Sorry?
Yes?
Physically, can we have two different channels for A and C to connect, to talk to the base station and for base station to talk to A and C?
Yes. Can we physically have different channels for A to talk to the base station and another one for the base station to talk to C? Yes, it's possible. If it's possible, you have logically two channels. You have physically two channels. Therefore, you have two mutual exclusion protocols. On each of the channels, there will be only one transmitting. But the two channels, if they don't interfere, if they are well separated in spectrum, it will be possible. Yes. Which is what happens between you and your neighbor. Hopefully, you're not on the same channel. I mean, if in the apartment that's behind the wall, you have another base station, you want to put them on different channels so that you have two different mutual exclusion protocol instances. If they're on the same channel, they will interfere with each other and only one will be able to transmit at a time. Even if you're not able to decode the packets of your neighbor because they're encrypted, but still they will prevent you from sending. Voilà, what I said is the theory of Ethernet, and for Ethernet today it's a myth. It's how Wi-Fi works, but it's not how Ethernet works. You've done in the lab wiring, logically, and with wiring we used switches. So Ethernet today uses switches and does not use CSMA-CD, except for very rare cases. So how do we come to this, and what are the different steps of the evolution? This is what we will discuss now. As soon as Ethernet was invented, which was invented by Digital, Xerox, and another company that I forget, the industry, the big industry, HP, IBM, etc., they wanted to do the same thing. So some of them took this idea and they started to port it to enterprises, not to campus. In campus, we do things. If it doesn't work, okay, we're happy. We have an opportunity to fix the problem. If you're a bank or an insurance company, you don't want the computers to not work. So the very first thing that people did when they ported Ethernet from the lab to the industry was this. You say, no, we're not going to pull a big cable that goes across all offices. Anybody can come and connect their computer to that. We need a more managed way. So the first thing that people invented was called the passive hub. What is a passive hub? Well, the idea is instead of having the big cable going everywhere, you put the cable in a box, one or several boxes, and then you have ports that you connect to. Imagine those are coax things, so you just screw them on it, and this will give some order into this potentially chaotic system which is similar to connecting your antenna cable to a socket. That was the very first things, and the only idea was to avoid cables that hang around, people walk on them, somebody who comes to do something on the wall might break it, etc. So it's nice, clean thing. But it's just, say, a real estate issue, not so exciting. The first exciting thing was to use electronic in this cabling hub. Electronic means instead of having physical wiring like we did before, but instead of doing the wild way, you do it the organized way, you do electronic, and in the language of this lecture, what we can say is this is layer 1 repeaters. Repeaters means you connect a cable here, you can send your Ethernet signal on the cable. An Ethernet signal, think of it as, for example, +1 or -1 voltages sent over the wires. Then you put a bit of electronic that decodes just those transitions. It doesn't understand the Ethernet frame, but it just sees the bits that constitute the frames and repeats them. So it decodes them and recreates the same signal on this bus of the box. Then it will here, when it sees a signal here, it will recreate the same there. So logically, it's the same as if we had a single cable, but there is of course a large benefit. is that the signal is regenerated at every point, so we can have a better signal, or, that was the goal here, have cheaper cables. Instead of having high quality coax cable, we can have here a small cable because the signal is recreated here, so the signal to noise ratio has to be the one that corresponds to a cable that is short, not a 2-kilometer cable. So that was the first value, to have cheaper cable, and today we use Ethernet on cables that are similar to telephone cables, twisted pairs. But the main advantage was to have management of this. Imagine you have your big Ethernet cable that is shared between everyone, and assume something goes wrong, like inevitably in any complex system, something goes wrong. What can go wrong? Somebody has put a heavy object on the cable, and the cable has been damaged. So instead of having a nice coax cable, you have a cable that has a different geometry. The signals can reflect, it can create intra-signal interference, and the thing doesn't work. The systems cannot decode because the cable is not okay. How do you fix the problem? Well, I can tell you, if this is this kind of cabling problem, it's a nightmare to fix. You need to go with a cable analyzer that you plug into the cable and analyze in the analog domain with an oscilloscope to see what's the shape of the signal and try to guess that there is a reflection somewhere and isolate where the reflection is. That was the experience with the very first Ethernet cables. So not so exciting. So industry people who thought of those concrete problems, they said, no way, we cannot do that. So with this technology, you fix the problem, because if any of those cables here are damaged, you can easily disconnect them, because this is electronic, so you just don't do a repeater, but there is a remote switch to the repeater, so you can disconnect this lobe, or that one, or that one. So by disconnecting them one after the other, which you can do remotely by typing commands on a computer console, then you can detect in which lobe there is the problem, you disconnect it, and then at least the rest of the network operates. It may look stupid, but that was the real motivation for what makes the network be like they are today. So it was the maintenance problem. Be able to have a network that is made of small segments that are point-to-point and can be isolated, because shared medium cables are a nightmare. Companies that run shared medium cables today are the TV distribution operators, and they have those problems. So they are trying to develop point-to-point alternatives to what they do, but it is known as one of the difficulties that they have in running their networks. So the main effect of this was that even though we still have CSMA-CD, the cabling seen from an individual viewpoint, from me and my PC going to the wall, to this socket here, this is an Ethernet socket here, I simply have a point-to-point cable. I have a cable between me and a socket. No one else is connected to it. Incidentally, we could use, as I mentioned, cheaper cable. So that was the second step of the evolution. Instead of having expensive coax, we could use twisted pairs. Twisted pairs, there's typically 2 wires to transmit in one direction. That's one pair. 2 wires to transmit in the other direction. So 2 wires to send, 2 wires to receive. And we twist them, because by twisting, 2 adjacent lobes have opposite orientation. So the electromagnetic fields that radiate from them or that are captured by them have opposite signs from 2 lobes, so they almost cancel. So the interference that this catches and generates, electromagnetic system are always symmetric. If you can receive a signal, you transmit the same signal, then they are almost cancel. It's less good than a shielded pair, but it also is a shorter cable, so that's good enough, and that's much more convenient. I will conclude with this last step. So far, we are ready to the main revolution in MAC layer, which was saying, well, forget about the initial design, forget about sharing a cable. Once we have a box to which systems are connected, And if we invest a bit of money into developing a smarter box, instead of having a set of repeaters that inside the box simulate exactly the operation of CSMA-CD, we can do something better, which is having frame buffers. So when this guy, A, sends a packet, for example, instead of creating a collision on the wires if someone else is transmitting, like you would do with these repeater boxes that are in the previous slide, here what you can do is receive the packet, terminate entirely the wires, not just repeat the bits one by one with electronic, but receive the packet, put it in a buffer, and if another machine is sending at the same time, because they use different wires, if they're connected to different buffers, the two frames can be sent in parallel at exactly the same time and received by the box. Of course, the box will need to process the packets and know where to send it. And if both packets are going to C, then they will not be sent together at the same time. So you will need a buffer that has space for more than one packet. In other words, you're making here a queuing system, same as a router. You have two packets that come in, you analyze where they need to go, and of course you know how this analysis is done. It's done based on the MAC address. You will send it to the destination. This is a bridge or a switch. Voilà, we'll talk more about what this means about making networks of bridges and switches after the break. So we resume in 13 minutes. On this slide here, there is Ethernet exactly the same way as if there would be no active hub, as if the cable would be shared. So a mental model of this is that this cable continues here, and when A sends a stream of bytes that correspond to a packet, the bytes are repeated and flooded everywhere on the network. In particular, if A talks to B here, C will sense a channel busy, or if by bad luck C starts transmitting at the same time, there will be a collision. So hubs force collisions to happen, contrary to switches here. Switches are practically synonym to a bridge. A bridge is an architecture name. It means an intermediate system of layer 2. A switch is a bridge, but a switch alludes to the fact that it's implemented in hardware. We will see in the lab that you can have a switch in a computer. You can transform your computer into a switch. In that case, it's called a bridge because it's just software in your computer. If you go to Migros and buy a little box that with 8 Ethernet ports, it's called a switch because it's a product name. But for us, it's the same. Bridge or switch mean the same. So a bridge is a system that is intermediate system of layer 2. Layer 2 means Ethernet packets, and it means it's able to receive internet packets on one port and forward them on another port. Here I'm showing a network with 3 hubs, so cabling hubs of the same time as before, that I have interconnected with a bridge. Of course, I could put the bridge in the hub like I showed before, but in this case, I put it at only one place. Then the main difference is that here there are now 3 collision domains. If A sends a packet to B, for example, this port of the bridge will sense that something happens and will not transmit or would create a collision. But if C sends a packet to D or E sends a packet to port 3 of the bridge, those 3 things can happen in parallel. There are 3 different collision domains. But there is a single local area network. This is a single LAN. A LAN is an architecture concept. It means a network at layer 2. Here there is a single thing at layer 2. We'll come back to that in a second. Bridges are transparent. So from the viewpoint of A, when A is sending a packet to E at the MAC layer, whether there is a bridge here or a hub, you can put hubs interconnected to each other, so you can create networks of hubs. There is no difference from a protocol viewpoint. Of course, we hope that there is a difference, otherwise we would not have invented bridges. The difference is performance will be better with bridges. But from a protocol viewpoint, if you do Wireshark, you will not see whether there is a bridge or not in the system. How do bridges work? They are similar to routers in the same they are packet forwarding machines. They receive packets, they analyze the header. In the case of interest here, they analyze the MAC destination address in the header. They find the destination address, they go to a lookup table. Here I'm showing the lookup table of this bridge in the middle. It has 3 ports, and it has a table that says for every possible MAC address that it will ever see in its life, on which destination it should send it. If, of course, a bridge can also see that if A sends a packet to B, the bridge will see it on port 1. So bridge are like Wireshark packet sniffers. They see everything because they are intermediate systems, so they're interested in packets that are not to them, destination to themselves. So if A sends a packet to B, the bridge will see the packet, will analyze the destination address. It will see this is B. B is on port 1. This is on the port on which I am receiving this packet, so I don't do anything. The packet is already arriving on the side. I would forward it, so there's no point forwarding it, which corresponds, if there is no bug in this network, to the fact that A, the source of this packet, is on the same port, which could happen with this version of Ethernet. How do the red characters in the title are here to illustrate the difference with IP forwarding. If a box is a router, it also has a table, but it goes to the table to do longest prefix match. Here there's no such thing. Why? Yes?
Because the MAC addresses are different from anybody.
Because the MAC addresses are different from anybody, because the MAC addresses are not structured. The MAC address are hardware numbers. So the fact that A, B, C, D are in the same network is not visible from the MAC addresses. The only thing you can read on the MAC address is the name of the manufacturer, for example. But the MAC addresses have no topological information for the network. So it's difficult, it's not possible to have, it doesn't make sense to do longest prefix match. There's no structure in this. So you need an exhaustive list. Of course, you don't have in a bridge the list of all the possible MAC addresses in the world. You have a list of only the addresses of interest. How is that built? Well, by packet sniffing. Bridges learn by observing the traffic. So when bridge here sees a packet sent from A, for example, it will read on port 1 all the packets. It will read the destination address, but also the source addresses. So if A sends a packet to anybody, the bridge will see this packet on port 1 and will learn that A is on port 1. If B does the same thing, then the bridge will learn that B is on port 1. Of course, the problem is for machines that receive packet and never send. Well, those machines will never be detected by the bridge. So the bridge this will not work, but that's an extremely rare case. Even streaming devices, industrial devices like PMUs that stream data to a phaser concentrator, and the communication is one way, but typically you still do things with the PMU. You still, once in a while, you update a cryptographic key, for example. You log into the PMU to update something. So once in a while, there will be traffic to the PMU. In the very rare case where B would be totally silent, for example, then the bridge will never know that B exists, so it will not be in its forwarding table, in principle. Of course, if you have such of those weird cases, I know only one weird case of that time. That was in the Geneva airport a few years ago. The display system for the TVs showing the flight information was by having a source that broadcast a packet to all the TV terminals with the latest flight information. And there was no ACK, no feedback. You simply repeat the same information again and again. If a packet is lost, you will see a garble on the screen, but the next second, a new packet hopefully will arrive that will refresh the thing. So the screens don't reply, at least in this old type of system. But in a case like this, you probably want to configure the bridge manually to do this. Or, if the destination address is not in the table, the frame is broadcast to all ports. So which is useful, for example, if A, to bootstrap things, when A talks to B for the first time, when the bridge sees that packet, it will learn where A is, but if B has not done yet anything, then the bridge will broadcast it to all ports. In the case A to B, that was useless, but if A was talking to D, then this packet will be sent to port 2 and to port 3. It will reach D. In the standard case, D will reply with an ACK or with something back to A, and the bridge will learn that D is on port 2. This is how bridges operate. So they use overhearing of source MAC addresses, and in the default case, they use broadcast to all ports, of course, ports other than the one on which the packet was received. Multicast is a special topic that we'll discuss later. On this network, if the box in the middle is a switch, which is what we saw before, or if it's a hub, you could also make a hub. So the hub will, as I said, can be interconnected to each other. The hubs are transparent. They are as if you would do physical wiring. So if this is a hub, it is as if the same cable goes everywhere in this tree fashion. If X is a hub or a switch, how many frames can be transmitted in parallel in this network? And I propose 4 possible combinations. I close in a few seconds. And Dirac on the correct answer. The correct answer is if X is a hub, it's like you have a single Ethernet cable, so there can only be one. If X is a switch, then you have 3 cables, and on each of those cables, there is only one packet that can be transmitted at the same time. So the answer is 3 in that case. Now, if you think about it, it's completely stupid. The answer should be 6 for the second case. If, at least if we replace the hubs here by smarter things, like the ones we had before, remember, when we replace a hub by a switch, we replace also the cable. This is an opportunity to have cheaper cables, and the cables are able to transmit and receive simultaneously in the same direction. So why do we insist to do Ethernet if we have switches in a network? Well, the answer is we don't insist. We drop Ethernet. That's a symptom of less is more. When we run CSMA-CD on Ethernet, for example, you connect your machine to a hub. Because it's a hub, there might be other machines connected to, and you are in a shared medium setting. So you have to run CSMA-CD. Now assume you connect to a machine, and this machine is not a hub, but is a switch. If you don't know it's a switch, well, you will connect with a standard Ethernet. What is the effect of the standard Ethernet when you have only 2 machines? Because in that case, you have only your PC and the switch. Everything beyond the switch is outside the collision domain. So you have only 2 systems. If 2 systems are connected together, there is never any collision. You can transmit in one and receive in the other. But if you use CSMA-CD, you will not make it possible to transmit in the 2 directions at the same time. Because CSMA-CD is made to avoid 2 systems to talk together, which makes sense if you're more than 2. But if you are 2, the problem is not of interest here. So if you use CSMA-CD, you force your cable to be what is called half duplex. Half duplex means the cable can work in both directions, but only half of the time. If you transmit, you make it impossible to receive. This is what happens if you use CSMA-CD on Ethernet cable. Of course, if you have a switch at the other end, it's stupid to do it, so the industry has quickly realized that it's stupid to do it, and they call it full duplex Ethernet. So there is a variant of the standard that says if you're connected to a switch, we make a little system in the Ethernet hardware that allows you to speak to the box, and you ask the box, are you a switch or are you a hub? In fact, you don't ask to the box, but there is a special sequence of tones or special signals that are sent. If you receive this signal indicating this is a switch, then you don't need to do CSMA-CD at all. You do nothing. You do a point-to-point protocol. You send your packet on 2 wires. You receive on the other 2 wires. And this has a name. It's called full duplex Ethernet. That means there is no CSMA-CD. This is step 4 of the evolution. Now, if you just look at the result of the evolution, you see that we call full duplex Ethernet something that we could simply call a point-to-point transmission line. So there is no reason for Ethernet, or at least in the sense of CSMA-CD here. But that's not the end of the evolution. We have seen that we can put several hubs and make a network out of them. We can do the same with bridges, and that's what is very often done. Here is, for example, a network where there are 3 bridges connected together. And we would like to hope that the method, remember, bridges are not configured, they learn their forwarding tables by simply observing traffic. Does it continue to operate if we arrange networks, if we arrange bridges in a network? Does the method of learning where MAC addresses are located work if there is more than one bridge arranged in a network? What do you think? I'll close in a few seconds. So the majority thinks yes, because learning propagates, but we have a strong minority that says only in special cases. Well, the correct answer is yes, in this network it will work. It will work. For example, if C sends a packet to Z, what will happen? B2 will see this and will learn that B2 is on port 2. Right. Now, if C sends a packet to X, B2 will receive this packet at the beginning. B2 will not know where X is, so it will broadcast it on the other 2 ports. So we'll go here where the packet will be useless. It will be deleted by Y. It will arrive to B3. B3 will do the same thing. It doesn't know it will forward it to B1. It will go everywhere, and it will eventually go to X. Now, Bx will probably respond, and the packet will follow the other way. When this packet is going, for example, from C to X, B3 has received it on port 2, and we learn that MAC address C is on port 2. So by the combination of flooding when we don't know and looking at the source addresses, we will see where the packets come from, and that's the correct decision. And that is true for this network, but it's less true for that one. What's the difference here? There are also 3 bridges, but now the topology is a loop. The previous topology was a tree, means there was no loop inside the topology. Here there is one loop. The entire topology is an entire loop, which means there may be several ways to reach the same bridge. Now, a bridge cannot learn where the packet comes from if it can come from several directions. So this method will not work. The bridge will oscillate, thinking the packet is on the left or on the right or on the left or on the right, so they will broadcast it in all directions, and the network will die of too much broadcast traffic. So the method of learning does not work if, at least simply, if there can be parallel paths to reach the same bridge. We need only to have a single bridge. So if we have bridges, we need a way to solve this problem. This is solved by the simplest of all methods. Like always, when you wonder how is the thing solved in TCP IP, always imagine the simplest. Very often that's the case. The solution is we force bridges to be organized in a tree. Of course, we don't physically prevent topologies like this one. Here is a topology which has a big loop and another switch in the middle. That's a good topology. I mean, we want, in many cases, to have redundancy in a topology. If you're wiring a wide area network inside a city, for example, a very common topology is a ring, because if you break one link or one node in a ring, there is always another path in the other direction. So it's a simple topology that always has an alternate path. Sometimes you don't care if it's just your local area computers in a department, you don't have critical servers, then perhaps you don't care about redundancy. But very often in networks, you want to be able to have some redundancy. So you want, if you have redundancy, you have loops. So the learning method of bridges will not work. The solution is bridges apply a protocol, which is called the spanning tree protocol, STP, where they talk to each other in order to build a tree. How to build a tree, there are several algorithms to do that, and if time permits, the last week we will discover it in detail. It's a very interesting protocol, but it's very easy to understand what it does, even if we don't know how it works. But in a nutshell, what they do is all the bridges talk to each other at the MAC layer. They have MAC addresses on all ports, so they can talk to each other and know who is saying what. The bridges also have a label, usually that comes with the bridge manufacturer, which you can also configure manually if you want. And the bridges talk to each other to elect a leader, the head of the bridges. And the leader of the bridges will be used to establish a shortest path tree using algorithms that we will see next week or the week after when we talk routing protocols, from themselves to the leader. And then all the links that are not on the shortest path tree are disabled. And by definition, a shortest path tree is a tree, as the name indicates. So by doing that, we will have a tree. I said the links are disabled. It's not exactly the links. It's some of the ports are disabled. For example, if the shortest path tree goes to switch 1 here, then this one decides that the shortest path to switch 1 is this way. Therefore, it will disable this port. It has 2 ways to reach it. It disables the one that is not the shortest. It doesn't really matter how they built the tree, but what really matters is to understand that the bridges constantly talk to each other to organize themselves in a way such that they will deactivate a few ports to make the active topology a tree. Now you can say if you deactivate some links to make it a tree, what's the value of having a ring here? And the answer is, of course, the spanning tree protocol adapts to failures and to changes in the network. For example, if this link breaks, or if this link breaks, then this will be detected by the bridges that will recompute a new tree. So if one of the links break, they will create another tree that will use one of the backup paths that is available here. So it is still interesting to have redundancy in a network of bridges. It will be used if there is a failure, but the redundancy will not be used to do load sharing. For example, in this case, if there is a packet that goes from a host connected to switch 9 that has to go to a host connected to switch 2, it will not use the direct link here. The packet will need to go the long way following the shortest path tree, the spanning tree. This link will only be used if something breaks somewhere, and so it's really used as a backup, not for load sharing. That's the drawback of bridges today. This is how bridges operate. Yes, question?
This is only working when, for example, hubs are not present, right?
Pardon me?
This is only working if hubs are not present. For example, if you have a hub connected with LAN and between switch 7 and switch 2 and you break this link, then you will isolate the hub.
So the question is, this is working only if hubs are not present. Well, not really. I mean, this line here is either a point-to-point connection or an entire system with hubs.
And if there's a hub present in LAN H between 7 and 22?
Between 7, where is 7? And 22? Yes?
So STP breaks the line.
So STP does not break the line. STP deactivates the port on the bridge. So STP will say, this switch will say, this port, I deactivate it, which means I never use it. But it's physically connected. But I will not use it for forwarding traffic. In particular, when I will do a broadcast because I don't know where to send a packet with a given MAC address, I will not broadcast on this port. But it's still, the thing still exists and works, but it's not used for anything interesting. An important thing to remember, if in doubt about how bridges operate, is that the bridges, the one that we see today, there were other bridging protocols that were invented, but they've practically all disappeared from practical deployment. This method of bridging is called transparent bridging. Transparent means, truly, it's transparent from a Wireshark viewpoint. If those two machines are connected to these Ethernet cabling systems, it is impossible to make a difference, to know whether this is a bridge or a hub or a complete network of bridges or a very complex thing, or if they are physically directly connected. This is transparent from a protocol viewpoint. Again, not from a performance viewpoint, obviously. So Ethernet hubs or switches practically play the same role. Of course, there are differences in if it's a hub. We will know if a packet is transmitting to the router here, and those are hubs, the packet will be sent everywhere. So this guy, if you have a packet sniffer here, you will be able to see all the traffic if those are hubs. If those are switches, and if we are in regular cases where the switches were able to learn the MAC addresses, when this guy sends to the router, the packet will go directly to the router, and here with your packet sniffer, you will see nothing. You will see only the broadcasts, but not the regular packets. So back to the same question as a minute ago, but now I replaced all the boxes by switches. The box in the middle, which could be a switch or a router or a hub, is a switch. The hubs that were here are now switches. How many frames can be transmitted in parallel? I close in a few seconds. And the correct answer is larger than 6. In fact, if all the links are full duplex Ethernet, which would make sense because all the boxes are switches, on each of those lines there can be 2 packets in parallel. The chance that that happens is perhaps not 100%. You need traffic to have a reason to flow, but it's possible that there is one packet that leaves the queuing system here going to D, while D has something to transmit here. And the same is true for all the lines. There are 9 lines, so there can be 18. There can be up to 18 frames being transmitted in parallel in this network. If the links are half duplex, which would be weird but can exist if for whatever reason this hardware does not support the full duplex, then there could be only 1 on this line, 1 on each. There could be 9 if the lines are half duplex in that case. This is why, of course, we have switches instead of having repeaters. The performance is much larger. But now if you think, yes, question?
Each switch has a maximum of 6 though.
Each switch?
Can have maximum of 6 packets in parallel.
Each switch can transmit 3 and can receive 3.
Okay, so when we say 18 or 24, we mean in the sum of the network.
Yes, in total, for the total network, yeah. If you think about it, this is how today a local area network is managed and cabled. But what are we doing? We have hosts and systems that are connected to packet switching devices that forward them by looking at the MAC addresses. If we put IP routers instead, we would have practically the same thing. Right? So in terms of performance, having a router here directly that looks at the IP destination address instead of looking at the MAC address would make no difference. Why do we have switches, and why do people continue to buy switches and not put routers everywhere? Is there a good reason? A router is more expensive, but there's no physical reason. I mean, perhaps it's true. But if you think about what a router is doing as opposed to a switch, it's exactly the same thing. It's a queuing system. It goes into a lookup table. In fact, the table of the router in a local area network environment is probably smaller, so it could be even simpler than a switch. Yes? A switch needs a huge forwarding table if it wants to connect to the internet. That's true, but in most things like this, you probably have a default route that goes towards the connection to your ISP. Yes?
Forwarding in switches is implemented in hardware.
Forwarding switches is implemented in hardware. That's a true statement, but is that a cause for... Could you not implement IP lookup in hardware? In fact, the high-performance routers implement IP lookup in hardware. You have, if you're a router not here, not at home or in an enterprise, but at the core of the internet, you have 500,000 lookup tables to look at, so you do that in hardware. You cannot do it in software. Well, it's true, this hardware is more complicated. That could be a reason. Another? So to remain in a private network, well, that's not a valid argument. If we use private IP addresses, we are sure we will remain in our private network. Yes?
On the IP layer, a router has more work to do. He has to answer to ICMP packets and other stuff.
A router has more stuff to do. What other more stuff does it have to do?
He has to load packets. He has to send ECMP packets to modify the sender.
It has to send ICMP packet if there's an error, but it's true, but you can disable it. You could do a cheap router that doesn't do ICMP, and some routers don't do ICMP for mainly security reasons. They don't want to reveal any information about their existence. You see those stars sometimes when you do a trace route. You see some intermediate steps, nobody responds. Those are routers that don't send ICMP messages. So it's a good thing, but I don't think it's the reason, it's the reason for that. Yes?
Is it because they're harder to configure?
Exactly. They're harder to configure. The bridges are plug and play. I mean, you buy a bridge from Migros. This bridge knows nothing of you. You don't do anything with the bridge. It will learn automatically the MAC address is connected to it. Whether you deploy it in California, in Japan, or here, it will work exactly the same way. Now, if you come with 4 routers here, you will need to do some configuration work. You will need to decide subnets, what is the size of the mask, which subnet you allocate to it. So you will need to do some configuration work. That's the main reason today. So bridges are meant to be plug and play. Routers in the current state with IPv4 are not plug and play. You need to design an addressing plan for your network. Of course, you could imagine that somebody someday does some software for automatically, at least for homes and small enterprise, to automatically make a numbering plan, in particular, as we have seen with IPv6, where you can acquire automatic link layer addresses. Yes?
With streaming systems like PMU, do you prefer bridges or routers?
With streaming systems like PMUs, do you prefer bridges or routers? There's no specific to PMU or not PMU.
Yeah.
Typically, many systems use bridges or MAC layer stuff because that was the state of the art 30 years ago, and some industries are moving very, very slowly. But there is no fundamental reason. I mean, all protocols today are TCP IP based and should work whether you are in a local area network environment only or not. We'll talk more about that in a few more minutes. Okay, that is the story of bridges and MAC layer. Now a few more technical details. Here's the format of an Ethernet frame, which you have seen. At least part of the format is visible when we do Wireshark. The part that's not visible is the preamble and the start frame delimiter. Those are bits that are not part of the frame per se, but that are here to detect the beginning of a frame. The physical layer sends bits. There are 2 ways to do a physical layer: a synchronous way and an asynchronous way. Synchronous means there are always bits being transmitted. There is always a transition, always something happening. And when there is nothing to be sent, the bits, there is somewhere an indication that the frame is empty. Synchronous physical layers are extremely difficult to do because you need to synchronize the bit clocks everywhere. This is done in some telecom distribution network. You need atomic clocks and a way to synchronize all the clocks. Ethernet, like all, I would say, more modern technologies, do not use this. Synchronizing the bit clock is the problem of, if I have it's a physical layer problem, I have a transmitter that sends a string of bits and a receiver that receives. Now to read the bits, you need to sample the system at exactly the same frequency as it was sent. So the frequency is given by the clock. All systems have a clock, an oscillator, a quartz, but they have some small difference in frequency, variations of 5 parts per million, which means 5 10 to the minus 6. That means when you read 1 million bits, the clock might drift by 5 bits. Right? Now, for this clock to give you the time, that's sufficient. It will mean over a day we'll have an inaccuracy of a few seconds, which is enough to come here on time for the lecture. But when you read bits, right, 1 million bits is very quickly done at 10 megabit per second. That's 1/10 of a second. If you're off by 5 times transition, of course, the decoding will not work. You're not reading the thing at the right place. So you need a mechanism to synchronize. You can globally synchronize all the clocks in the network, or, like Ethernet do, you can synchronize per packet. When a packet transmission starts, you have a special preamble, a special activity that you try to detect in the noise on the line. And you build a special circuit that will detect the shape of the signal and will reset the local clock to exactly the transitions that are observed on the signal. So it will reset the local clock for every packet transmission. When the clock is reset, the packet is small enough so that you will be able to accurately decode the entire packet. Which means that there must be a small gap between packets. When you finish transmitting a packet, you must not transmit anything, then retransmit this pilot signal here. And this means also that this pilot signal is not visible when you do Wireshark, because it's not something you can actively decode. It's just a special string that allows you to start. Other than that, the things that are in the Ethernet packet are the addresses, source and destination and source address. The type, that's the vocabulary used by Ethernet. It means the protocol type. It says what is inside. And for us, most of the time, what's inside is IPv4. It can be IPv6. Now we see that IPv6 is a different packet type seen from Ethernet, which means that IPv6 is not a new version of IP from the IP viewpoint, but is really a different protocol. It's treated as a different protocol. We spoke about that already. IPv4 and IPv6 are two incompatible things. It is in a different protocol. Now, IPv4 and IPv6 are practically the only protocols we see today, practically, but not entirely. There is a few hundred other protocols that have only extremely anecdotal importance. Some of them are, for example, one we've seen is ARP. For historical reason, ARP is not inside IPv4. But that's a historical accident. There are other things like MPLS that we will discuss a bit later. There are special things for special networks. And there are special things that cannot be done very well with IP. For example, high precision time synchronization protocol and other historical things. In the past, in the 80s, Apple has its own protocol that was not IP. Then there was an Ethernet type for Apple. There was one for Novel Netware. There was one for HP protocols, etc. Every IBM, etc. Each of them had their own protocol. But today, this is not really used. There are different Ethernet packet formats. This is the most frequent one. In the lecture note, I give an example of another format called the IEEE 802.3 packet format, which differ a bit. They are more complicated, and the complication is practically useless, but is historical. As you see, there is no indication here of the packet length. And so the hidden assumption is that whatever is contained inside an Ethernet packet must have an indication of its length if we use this protocol here, which is the case, for example, for IPv4 packet or IPv6. At the end of the packet, there is a code. It's called a frame check sequence, which is an error detection code. It's able to detect a few bit errors and able to correct single bits. The Ethernet mentality is we deliver a packet without error or we don't deliver it. So if there is a bit error, which on Ethernet system is extremely rare because this is on cable system, wireless transmission are a bit different. Errors are more frequent. If a packet has an error, it will be lost. It will be simply discarded. Voila. Voila, that's the end for today. Tomorrow, you will be able to start the lab on this topic. See you tomorrow.